considering the last one was like 30 questions and everything, I doubt like the practice quiz was what he said. It was an example of what you can expect from the MCDE type problems.
Right.
But if anything, I would expect like one or two of those MCDEs. So like literally like two different types. Like maybe one's got no spatial dependence and one's got no time dependence, like we saw in the homework. Like question 1 and a question 4 or something.
Okay.
And then instead of like the practice quiz where it had like 14, mini sections, instead it would have maybe 7 or 8. Because some of those like 14 mini sections didn't have to be there. Like
right.
Actually, yeah. So I think we'll probably have like 1 or 2 MCDE questions, and they're going to be different solutions for each one. Like they're not just going to both be the same variety. And then maybe a couple like quick theory questions. But we can't really predict those, so that's just general knowledge. Yeah. So that's what I think at least. But so since this one's like wanting to talk, or the purpose of this Zoom meeting is to discuss the boundary and the initial conditions. The best like sample for that is his
Well, can you start off like when I start off, but can you go through some that also like I know when I went through the homework, some of them didn't have any initial conditions because you know what I'm saying, the way the problem was, and then some does have initial boundary conditions, right?
Like question 1.
Like question 1.
Well, question 1, the initial condition was 0.
Yeah, there are some that seem like they don't have initial conditions, but they still do. It's just that the initial condition is obvious to you when you like look at it, so you don't even consider it as such. Because as I said in the first one, that type of question, like a number 1 or the one on the practice quiz even, the initial condition is for time, and it kind of makes sense that, given no time passed, nothing's been generated. So even though it counts as an initial condition, like in all of these problems, initial conditions do exist in every single one. It's just a matter of whether or not they're super, super important. Because for the most part, initial conditions are used solely to solve for your A value or your A and your B value, and that's it. When it comes to your general solution of your formula, whether that be a solution without the time derivative or whether that be a solution without the spatial dependency. So, yeah, so question 1 on the homework was, when it says specify the initial boundary conditions, the answer for that would be, since there's no spatial dependence, there are no spatial boundary conditions. So boundary conditions are for spatial dependence, and initial conditions are for time dependence. So for any given solution, you're only going to have one of those. You're either going to have initial conditions or you're going to have boundary conditions.
Well, what number are we looking at right here? Number 3?
No, this is homework 3, just quiz 1. I just pulled up the paper in my hand because this isn't something that we need to see. It's just something that needs to be explained. Because like regardless of the question, like because you were asking like you wanted to see an example of like question 1 in the homework, where it didn't have boundary conditions, and you're right, it didn't have boundary conditions, but it did have initial conditions. So regardless of the question, whether it be without time or without space, it's going to have a condition of a type. It's just going to have its condition that corresponds to what it still has. If it's still got time, it's going to have initial conditions because that initial is relating to time. And then if it's got space, it's going to have boundary conditions because boundaries are relating to a dimension of some sort. So like specifically question 1 on the homework 3, the boundary conditions don't exist because the spatial derivative doesn't exist here. So there are no boundary conditions, doesn't matter there. But then we do have to say, since there is time dependence, the temporal boundary conditions, that's what I said there. You don't have to write it like that. That's just me being weird. And then our at time 0 is the first boundary, and then at time infinity is the second boundary in terms of time.
This is for question 1?
This is question 1 on the homework 3. That's what I wrote.
Okay.
Well, hold on, I got a quick question. So you saying that when it's uniform, there's no spatial, right?
Mm-hmm.
So that means there's going to be no initial conditions.
There's going to be no boundary conditions.
Boundary conditions.
Yeah.
Okay.
Initials for time, boundaries for space. Yeah. So for each of these questions, regardless of the question, there's only going to be one or the other. You're not going to see both. It's not possible to have both because we don't know how to solve that, because that type of simplification is something we're not expected to know how to do. It's probably possible, but we don't know how to do it. So we don't have to consider it or care too much for it. So that's just going over something like that. And the thing is, the only thing that we're actually super interested in is the fact that it starts at time 0. And this is like a formality. If you ever have like a time, like one that has time dependency, your boundary conditions are probably going to be, unless specified by the question, which we haven't seen one like that and we probably won't, it's going to end up being time equals 0 is equal to something, probably 0, or it's going to be equal to either 0 or your max excess carriers of that minority, whatever that may be.
So to find the initial condition at time equals 0, you plug it into the general equation.
The general solution equation, not the general simplified, the general solution, the one with the e's, the one with the not like the e to the x's.
And there would still be a's in those answers, right?
Yeah. So that's the whole point of that. So let's go up to where is it? This is here's this is the type that we use to solve for the one in the practice test.
Yeah.
The practice quiz, as well as the one that's solved for question 1. This is the general solution you'll see. You'll see this. In every single problem, you are most likely going to be given GL, your tau values, and that's basically like all you'll super need. You'll also be given like some other stuff for other stuff. But for this part, you're only really going to need GL and tau. This is what your simplification becomes. And it is possible right here, it says GL may be 0 if the sample's in the dark. So that's also possible, but not super important, because obviously if it's in the dark, you just get rid of that and you're good.
Yeah.
What happens here is you put in, let's say at time 0, we want to find the value of A. And let's say that this value right here, GL tau P, just equals 10 to the 10th. We'll just say that here.
Yep.
You want to find A at time is equal to 0. Well, you just plug in 0 up here. E to the 0th is 1. This is equal to 0.
So I guess so if it's steady state, you just have to assume at delta P of 0 is equal to 0.
Steady state is different than at 0. So at steady state, in an example like number 1, or in an example where the light's being turned on at time 0, because it's a different ruling. Because when a light's being turned on at time 0, your graph goes from 0 up to the carrier, density that you reach, and then if your light's turned off, it goes from the carrier density it was reached in some given time.
So whenever the light's turned on, that's when delta P of that value will be equal to 0. Is what you're saying?
At the instant, so we can go to the practice quiz for this part, because the practice quiz had
let's
question. Yeah, it had that question. Over here.
Cause I was watching the lecture, and even he said, I think he was like, the hardest part of this is probably going to be initial and boundary conditions.
This
one. It's most confusing.
So right here, where was it? So here's the question here. So this one tells you it was in the dark and under thermal equilibrium for time less than 0. So I explained in the first one, the question 1 at time less than 0. This is like what we've been doing before this quiz, before MCDE. You just use the law of mass action because it was at equilibrium. Nothing's happened here. Because this one is waiting for you to turn the light on. So at a time less than 0, it's just going to be using law of mass action. That's just plugging and chugging with this number.
Law of mass action is P equals Ni squared over N?
Yeah, in this instance, yeah.
And what is N in this? ND?
Yeah, ND would be N.
Okay. Right, because it's an N type, right?
Yeah. And you can see that illustrated here. N and ND are the same. That's why the answer is 1.
Okay.
Yeah. But then over here, when we finally get to where it asks us, like, here's the simplified MCD, and you see that this takes a different form than the A that we saw. That's because right here is where you figure that out. The initial condition of the MCDE in terms of, excess carrier at time is equal to 0. And time is equal to 0 right here is where the light source turned on, because greater than or equal to 0 is when the light source is now uniformly illuminating your surface. So this is what we end up with. We solve this simplified one, and we get this. And the reason that you can say it looks like this, like GL times 1 minus this quantity, is because right here you can see that the initial condition because we're working with time, For the MCDE, in terms of delta P, T is equal to 0 is equal to what? It's equal to 0. And the reason for that is because, yes, while the light is on in this instant, there has been 0 time for the light to actually, exert its energy and generate carriers. And this whole concept of the reason that we can say this is because, tau P exists. This lifetime, how long it can exist, that shows you that there's an amount of time it takes for something to be generated or recombined. There is some amount of finite time that is required for a generation or a recombination to occur because we're not teleporting.
So we have to have time. So right, since T is equal to 0, that means there's no time at all. So that means it has no time for anything to happen.
Yes, that's straight up it. Yeah, that's it.
Is this the case for any type of not just uniform?
Not so. This is something different because obviously if it's not uniform, then we won't have time because as I said, you can only have one condition or the other. You either have boundary or you have initial because you won't have both because we don't know how to solve it if we can't cancel something. So when it comes to time, you'll have two distinct possibilities. You will have P at time is equal to 0 is equal to 0 when it's a question where the light's being turned on. So your graph ends up looking like 0, 0 up to GL tau P.
Yeah.
Wait, so what if it was an actual number? Like what if T equal 1 or T equal 2?
Then what you do is you take this equation, because remember, the initial condition is what you use to solve for this equation technically. But you instead, once you have this equation, and like here, we can go down to one where it just gives you a time, like this right here. This gives you a time, and then there's one that gives you a time at like the microsecond range, and you see I was off by a very, very big number. And that's the power. But the thing is, when given a time, then what you do is you simply plug that time into your solution, and it all solves out for you, and it'll tell you.
Okay, cool. Because we'll just plug in the time for T, and then TP is given to us in the problem on top.
Yeah,
right?
There's straight up one variable in these questions. That's why the solutions are so easy, because all you need is one piece of information once you have your solution.
GL is given to us too, right?
Yeah, it should be given to you every time. So looking at this, so there's two possible scenarios for this, as there's I think there's a couple possible scenarios for boundary as well. If you're turning a light on, if it's a question where the light goes on at time is equal to 0, you're going to start at 0. There's been no time for anything to happen. But conversely, if instead a light's being turned off at time is equal to 0, instead of it being equal to 0, it's going to be equal to GL tau P every time. If the light goes from on to off, it was on at its maximum value because you're treating it before you turn the light off, it was at the steady state. That's what you have to assume every single time for those questions, and it'll most likely tell you that. But when the light was on for some long period of time, it's going to be at, its maximum value because it's had all the time it needs to adjust and get to its, steady state. And that steady state value for these questions is going to be GL tau P every single time. And you can see that right here because of the way the equation works. Eventually, once you get past very, very small values of T, any basic integer value of T from 1 to infinity is going to bring E to 0. Because it's going to be some ridiculously huge negative number that essentially approximates this whole thing to 0. So given some infinite amount of time or finite amount of time, it's just this whole equation just works out to be GL tau P. And since you know that, if your initial condition is starting from some steady state and turning off, what's going to happen is your boundary condition, instead of being, change in P at T equals 0 is equal to 0, it's going to be change in P at T is equal to 0 is equal to GL tau P instead. So those are the two possible scenarios for this type of question. If it's turning
wait. And which occasion would it be when you said GL tau P equal GL tau P? What occasion would that be?
So at time is equal to 0 for a question where the light is turning on, it's going to be essentially the 0.00. But for the question where the light is turning off after some steady state time has been reached, some steady state carrying capacity has been reached, it's going to be at time 0, it's going to be equal to GL tau P every time. There's not going to be intermediate unless it specifically tells you, and we haven't done a single example like it, and I doubt we will. So it's going to just be GL tau P instead. So those are the two possible initial conditions for a time question.
So on your formula sheet, are you just writing down what the simplified MCDE, like the answer to question 5, are you writing that down for steady state? Because it's not going to change. Or sorry, not steady state, uniform.
Yeah, for this one, you can write it down like this, assuming that the light, assuming it's not in the dark, and it probably won't be in the dark.
If it's in the dark, how would it change?
The GL tau P would be 0, so it would look like this.
Oh, right, because GL would be 0.
Yeah, you'd cover up this, and your solution would be AE times 10 to the negative t, and that's something completely like wacky. Like we've seen it, and you can do it. It's just like that's then based off of your initial conditions, and you want to know what that's for? That one, when GL 0, that's when the light goes off, when it goes from on to off. So you know why that's useful? Because A is still going to be equal to GL tau P. It's still going to be equal to GL tau P because it started at some high value. It's now lost its GL tau P. So it's going to have to go from that value times some, operator that causes it to decrease at a steady rate at an inverse E. And that's what it is. So A should in these scenarios, when it's a temporal, like when it has no spatial dependency, the A, unless like it's a complex question we haven't seen yet, the A should always just end up being GL tau P.
Okay.
Regardless, whether it's in this dark or whether it's in the light, it should always end up being GL tau P.
And how do you do number 6, if you don't mind?
Number 6 where?
On the practice quiz.
Yeah. Okay.
I also had a side question when you get done with number 6. Well, I was you get it. Never mind.
Number 6. This one's easy. As you can see, it looks like I did terrible on this, but it's because I refused to do it correctly. But either way, this one, that's number 7. This one is calculate P over Ni at t is equal to 1 second. So you have to find P. So what you do right here is you plug in 1.
Okay.
And when you plug in 1, as I said, any type of normal integer value you'd see, it's like -1 divided by 10 to the -6. So it's going to be some absurdly big negative number. That's no good because e to some big negative goes to 0. So what happens here? This ends up being GL tau P. So you end up having
Ni.
Yeah, GL tau P over Ni. GL tau P in this scenario, what was it? It was 10 to the 12th divided by Ni, which is 10 to the 10th. That's intrinsic. It's a constant we're given it, or we know it.
100.
Wait,
so it ends up being 100, as you said.
I see.
So since you said that since t is going to be 1, according to number 6, t is going to be 1, and tau P is going to be bigger than 1?
No. Tau P is smaller than 1. We know tau P. Because what you do with this, when it says calculate P over Ni, what you're really just doing is calculating a P and then dividing by Ni. So you calculate P first, you plug in 1 into this equation, it spits out GL tau P. That's what your answer is.
Well, exactly. What I'm saying is, how is it to where like this inside right here cancels out? You said that's because it's going to be a real big negative number, which makes it 0?
It's basically
So how that works is this is just like the e to the x rules here. So if you have e to negative x, as x increases, e approaches 0. So in this instance, you can treat this whole thing like because what happens here is if t is some large value compared to tau P, it's going to end up being 0. Like the whole thing's going to end up being 0. Because 1 is like infinitely, like is for our purposes, it's so much bigger than 10 to the -6 that, 1 divided by 10 to the -6 is going to be a pretty big number. Slap a negative sign on that pretty big number, you'd have something like e to like the millionth, e to the -1 million. E to the -1 million, basically 0. And because of that, if you do 1 minus 0, it's equal to 1. GL tau P times 1 is GL tau P. And GL tau P happens to be 10 to the 12th here. 10 to the 12th divided by 10 to the 10th is 100, or 10 to the 2nd.
Yeah, I just put e to the -10 to the 6 in my calculator, and it just gives you 0. So, yeah, it just becomes 0, like you said. And then you just have GL tau P So the P at time 1 is equal to just GL tau P.
Yes.
Which is 10 to the 12th.
Mm-hmm.
And then 10 to the 12th divided by 10 to the 10. Okay.
And that's why you get 110 to the second.
Nice. Okay, cool.
Yeah. And then over here, question 7 is identical to question 2. It's a trick question. We talked about this last time, but for every single one of these MCDE problems, it's assumed that we are at, what was it? It was like low injection or something. What was it called? Does anyone remember that? It's somewhere in
yeah, low level injection.
Low level injection, that's what we're looking for. So that term, low level injection, essentially tells us that the majority carrier, regardless of changes in the MCDE, will not change. Its changes will be negligible. So like throughout this entire problem, ND and N are always going to be 10 to the 18th. Hence the reason that even at, some time or some steady state, it's still going to be 1. The same way it was 1 when nothing had happened yet. So nothing changes for the majority carrier. So we can go back here because now we have to talk about initial conditions with regards to spatial, and this one's trickier.
Yeah, and that's what I was going to ask you. I was going to ask you, like, right here, when you see right there that delta P of T equals AE to negative TP. Okay, so how do you know when you're going to have 2 variables and when you're going to have 1? Like, how you going to know when you just have A, or like right here in the second part, how it has A and B? Can you tell that just by reading as soon as you read a question, do you know in your head if it's going to be just 1 constant or 2 constants? Does that make sense?
Yeah. So far, we have not had I don't think we've had one where B ended up being a number. B always ended up being 0. And I think that's probably going to be the same here because there's a reason. The only difference between, besides A and B, between these two parts of this general solution to like a spatial dependent problem is the fact that there's a negative sign on the X for A, and there's not a negative sign on the X for A over here. Also the fact that LP, remember LP is this quantity, it's not like the same. So like on the formula sheet, make sure you like say that. But, and it also has this part. So here's the thing. And this has the same rule. If you're in the dark, this goes to 0, just like it did last time. So we did an example like this. I believe it was in Q3, maybe? Yeah, it was in Q3, it looks like. So in question 3, yeah, question 3. So I have that out now. On the homework, we did something like this.
Can you pull the homework question up real quick?
Yeah, I can find it. Oh, and it pulled up the thingy again. Come on, go away. Go away. I didn't know we had 9 people. I just looked at it. That's a lot of people. It's over here. It was under here, there. All right. It was homework question 3, so I'm going to make this big. Nope, went too far. All right, so in question 3, we can start picking out initial conditions. So right here, it's illuminated uniformly so that you have this value, and it tells you something. And then what it tells you is right here, when it comes to a major difference between time-dependent functions and spatial-dependent functions, a time-dependent function is technically P of T, like change in P of T, and then a spatial-dependent will be change in P of X. So there's a difference there. See, in a time-dependent function, you'd be given questions like when T is equal to, and then in spatial-dependent questions, you'll be given when X is equal to this. So that's another way to tell if you somehow messed up on figuring out which thing has to cancel, which is already pretty difficult. Last time we talked a little bit about how there's like limitations in the medium of the test, and that makes it easier for us for certain questions, like, the big equation simplification questions. So what we can see here is that you'll be given an X or a T, and using that you can also assist and infer if you made a mistake earlier on. But that's not the point here. So this tells you the surface at X equals 0 is damaged so that the minority carrier lifetime is 0. And for X greater than 0, the minority carrier lifetime is this. So you say, assume the level injection prevails, obtain an expression for the electron. So just like solve it essentially. And it's also under steady state conditions. So this is why we were able to get rid of time in the first place. It said steady state. So we don't have to care. There's no time dependence. It's already reached some constant value. So it goes to 0. So what happens is with this question, the information we're given is that at x equals 0, the minority carrier lifetime is 0. And then anywhere beyond that, greater than, the minority carrier lifetime is, some constant value. So you can come down here and you can look, and then it says solve the specify initial and boundary conditions. Here for initial, you'd say no initial conditions. It's not time dependent. And then for boundary conditions, obviously we have an A and a B. So that makes it a bit tricky. So what we know is and this is this one happens to be change in n, not change in p. So at change in n of x equals 0 is going to end up equaling a plus b plus gl tau n. And we can go back to this real quick. So let's say this was equal to 0 at x equals 0. So what happens at x equals 0? Both of these things go to 1, right? E to the 0 and e to the 0, these things are going to both go to 1. So it's just going to end up being a plus b plus, tau n or tau pgl. So that's the first step. You plug in the condition, simplify your equation further to start thinking about what the next step is. Now, this is more of an application in theory, because what he said in the question on the homework is that at x equals 0, the surface is damaged. So the minority carrier lifetime is 0, thereby meaning that at the surface, regardless of how much light you decide to just throw at it, not a single carrier, will be produced. No generation, no recombination, nothing happens. Because of that, you can continue to say, so as I said, it's going to end up being like change in n is equal to a plus b plus gl. Well, now, since you know that nothing can happen, you can get rid of that change in n equals to x and set that whole quantity equal to 0. So now you have 0 is equal to a plus b plus gl tau, like tau n or whatever. And you can do that because in this question, he tells you that at the surface, there's no carriers. That's what this means. No carrier lifetime means no carriers. So at the surface, no carriers. Therefore, your change in n or your change in p is going to equal 0. There's no carriers there. So now that you have 0 is equal to a plus b plus gl tau n, or whatever you want to say there, gl tau, we'll just say, you now have to figure out, you got to use that to solve for something. So right off the bat here, when I was doing the homework, I left it there and I moved on to the next portion because solving that helped me understand it a lot better. Because what ends up happening here is what you can see in the next part. Because our boundary conditions is, x is equal to 0, and then x is equal to some arbitrary large number. It says semi-infinite, uniformly doped, whatever. So I just said infinity, but some arbitrary large number is what you want to use. So at infinity is fine. So for your next part, at n is
I don't understand why you're using like a real big number or infinity. That's for the part, right? So how did you tell in the problem that you was going to use infinity?
So the reasoning behind that is because it says a semi-infinite uniformly doped silicon wafer. So a semi-infinite is basically just a way to tell you like it's not finite by our terms. Like, yes, it's semi-infinite or whatever. It's just saying that like this bar for our purposes is some non-existent infinite bar that has no actual dimension. It just goes on. So this is for like the thought, because in real life, obviously, there's very, very obvious, dimensions to work with, and there's differences there. But here we just use infinity. But as I said, you could arbitrarily pick a large number because the result is the same as long as you pick a sufficiently large number. Because what happens is, let's go back to this formula now. Last time when we plugged in 0 to the simplified version of this, it ended up being a plus b plus tau pgl. Plug in infinity here, what happens instead? Well, you're going to get different values. You plug in infinity, it's going to be a times what happens to when e is at some absurdly large number. This approaches 0. So a ends up being 0 here.
This is where I got really confused because then
this is tricky.
You have b times e to the infinity,
and
I'm not sure what you're supposed to do with that to find b.
So on the thing, so this is just like straight theory. When you see this, it's just like what I tell you here is just the same like thing you apply across the board. So GL tau P Oh, wait, yeah, I should specify this. So at some arbitrary distance, some infinite distance away, remember how last time we said because it's damaged, there's no carriers? So instead of just saying, change in n at x equals 0, we can say change in n at x equals 0, replace that with just 0 because there's nothing happening there.
Yep.
So in this time, we do the same thing. And we replace, the change in p at x equals infinity with something. And we replace it with tau pgl. Why? Because the only change here is the fact that at x equals 0, there's nothing. And then at x greater than 0, it's a constant, the carrier lifetime's constant. It's the same everywhere else. So at, your arbitrary distance, your arbitrary big distance, you just approach it like it's like max value. And the max value you can approach is tau pgl here. So what you have instead of 0 is equal to a plus b plus tau pgl, you get tau pgl is equal to a, which is zeroed here as like, if you put infinity, so it's going to...
Hold on, I got a question for you though.
Yeah.
Okay, so I understand the part when you did okay, so x is basically infinity, right? So the ae to the negative infinity would be 0, right?
Yep.
But when you do the be to the, so when you do there's no negative in front of that be. Yep. So it's going to be just e to the infinity, right?
That's what he's doing right now.
Yeah, and that goes to infinity, and you'll see what happens here. And this is why I did, instead of finishing up the x equals 0 and solving for one of them, I instead moved on to this one first, because this one really like tells you the answer. So what happens here is we now end up with an equation that has tau pgl is equal to, a got zeroed out, so it's equal to tau pgl is equal to b times e to the infinity, which is infinity. So b times infinity plus tau pgl. What does that tell you? How can you get tau pgl is equal to tau pgl plus b times infinity? What does b have to be equal to make that function make sense?
I guess it has to be 0. I mean,
yes.
You could even try to work it algebraically and say, okay, you have tau pgl on one side, tau pgl on the other side. Subtract both sides, it becomes 0 equals b times infinity. And you can divide both sides by infinity.
Yep.
And 0 divided by infinity is
whatever way
0.
you want to work it, it ends up being 0.
Okay, I guess that makes sense.
Wait, so did you have tau pgl on both for the equal sign? So you did tau pgl equals... Yeah. Okay.
So the reasoning behind that, so remember in the last one when we were solving for, like when we said x equals 0 instead of x equals infinity, like the change in n at x equals 0 ended up just becoming 0. And we can say that because, at here, let's go back to this. Because we can say that right here it says at x is equal to 0, it's damaged, so nothing's produced. There's no carriers here. Regardless of how much energy you put in, nothing happens. So, your change in n or your change in p is simply a measure of your excess carriers. Therefore, your excess carriers at x equals 0 is 0. So you can set that side of the equation equal to 0. And that helps you solve for it later. But then that same thing works for this. So when you go some arbitrary distance x away from 0, and we just say infinity because we can, instead, the thing that's changed is that now we have a carrier lifetime. That's all. That's the only thing that's changed. There's a spot where we don't have carriers, and there's a spot where we do have carriers. Because of that, we can instead say that, at our carriers at x is equal to infinity is equal to the maximum amount of carriers. Think of it as like when it comes to spatial dependence, x equals infinity is equal to like the steady state of spatial dependence. So it's going to approach GL tau p, or GL tau n, or GL tau, we'll say is a general version of that. So that change in excess carriers at x equals infinity is going to equal GL tau p. And because of that, that's how you get the GL tau p on that side. Your A value is 0s, your B becomes B times infinity, plus GL tau p. The only way for that to work out is to have B is equal to 0. So B equals 0. And then that means if you go back to the original function where we had 0 is equal to A plus B plus GL tau n, this is for question 3 on the homework, you plug in 0 for B, what does A have to be? A simply has to be negative GL tau n, because you got to make it equal to 0. And all that math, all that algebra, all of that's to solve for the initial conditions or the boundary conditions.
Okay, I think I get it.
So that's like the main way. And I honestly predict, like, odds are, so let's look at question 4 real quick. So question 4, so here, like, here's another thing. He says along, and he just says or semi-infinite. So for our purposes, you can always just say x equals infinity for these questions as your ladder boundary. You can always just throw in an infinity because that's just how we're working with it. So this one is the inverse of what we just did. It's a little bit different because look, no light penetrates into the interior. So we think of it here as at x equals 0, x equals 0 is where we are at GL tau p, or in this case, change C. That's what they say here. That's what they ended up saying. Because this is just telling you the amount of carriers that are being produced there or whatever at x equals 0. In this case, in question 3, we had no carriers at x equals 0 and GL tau p carriers anywhere else. In this case, we have, we'll just say GL tau p carriers at x equals 0 and no carriers anywhere else. Question 4 is just the inverse of question 3, just the reverse situation.
Why is it? So for the last one, it was damaged at x equals 0. That's why it was 0.
Yeah.
But this one
just says no light penetrates. It doesn't say damaged. It's just telling you that from this interval, x like 0, x is like greater than 0, less than infinity. No light gets past. Like think of it like no light gets past the first layer of atoms on that bar. Even though, so like at position 0, there's one row of atoms who, is greedy, takes all the energy, and none of it goes anywhere else. They take it all. And that's how that works there. So that's just the inverse of that type of question. And this one, question 4, I can look at that one. I'm pretty sure the boundary condition solving on this one is also similar.
It'd probably be B is 0 and A is negative tau p GL, or is GL gone for this one?
No, because think about, so the nature of the nature for this formula. So yeah, GL's gone. You're right, GL's gone. But so here's the trick. Because of the nature of how the formula works and the fact that you have a negative x and a positive x, which is the main difference between them besides the A and the B, because of the nature of how that formula works, regardless of these boundary conditions, B should always go to 0. Because when something reaches infinity, B's got to be 0 to get rid of that infinity. So that's something to remember. If your B has a number, you did something wrong. It should be 0. It should be 0. And because of that, since B is most of the time 0 for the examples we've seen, that means that A is going to end up being, the negative value of your excess carriers. For the most part, it should end up being your negative value of your excess carriers. But in this case, it's not. Here's the difference. Last one, it was negative because it was equal to 0, right? At 0. This one, question 4, it's not equal to 0 at 0. It's equal to 10 to the 11th at 0. Therefore, your A is equal to 10 to the 11th. It's equal to the positive value of GL tau p. So when you're in the inverted scenario, think of it, the only thing that inverts is the sign. Everything else, and in this case, as you said, GL tau p goes to 0 because there's no light, past that portion. So yeah, that's how that works. So are there any, does anyone want any more clearing up of how boundary and initial condition stuff works? We could look at one of question 2 or something. We didn't look at question 2 and try and work it out. This one, as you can see, as I said, if it gives you a time, and it gives you an X in any of the question, looking at just the question, seeing that, you don't even need to know anything about it. If you see an X or a T, you can already know what dependency is going away, right? If you're given X, you're obviously getting rid of time. If you're given T, you're obviously getting rid of space. So that's a test taking and just question reading loophole for these things. Knowing that, you can automatically get a right answer for simplification of your formula. Not solution necessarily, but
wait. So the initial condition for 4 is going to be 0 and infinity, right?
Yeah. So you always do So the thing that changes with initial conditions, so for time, your time's always going to be when time's equal to 0 and when time's equal to some arbitrary large number, we always use infinity. And then for your x, it's always going to be x equals 0 and then x equals arbitrary large number, we use infinity. The thing that changes depending on scenario is your y value that's produced from that. So think of like what they give you is literally like your independent variable that results in the dependent shift of your y. Think of like the solution of these problems as a point where like it's like, let's say it's a time dependent. So your point is t comma change in p or something. So whatever happens in t, your change in p is going to be something. So at like on the quiz, when we look at the quiz, where was it? At time 0. At time equals 0. So for the quiz, our point t comma, change in p is 0, 0. And that's the way I think of it, just because that's how I do that stuff in math. It's like 0, 0. It's equal to 0. Here's your x, your dependent.
But for this situation, when we do our
this one or
0,
this one?
Yeah, for number 4. I mean, what's our answer? Our answer to that initial condition is going to be. It's not going to be 0, is it? It's going to be 10 to the. It's going to be delta c.
Yeah. So as you said, so at 0, it's equal to this. A ends up being equal to this. C is equal to c times 10 to the 11th. And then at arbitrary infinite distance, it's equal to 0 instead.
How do you know that it's going to be 0? Is that also given? Because I'm reading
it now. So this kind of is given because it says no light penetrates into the interior past 0. Thereby, anything past 0, no light's gotten there, nothing's changed. So there are no excess carriers produced. So that's how you know that. That's how you know where your 0 point is. Think about it this way: for most problems, you will have a 0, 0 as either your beginning or ending condition, regardless of scenario, whether it be space. Well, but not like you'll have a 0 like result somewhere. You can either have a 0, 0 or an infinity 0. You'll have one of them in every single scenario. You always have a 0, 0 or an infinity 0.
And for 3, it tells you that at x greater than 0, it's 10 to the negative 7th, right?
This is the lifetime carrier. That's not the p value or something. But yeah, you use this to calculate it. Because what this is telling you is that any beyond that, nothing can happen, because without minority carrier lifetime, nothing can happen. And then it gives you a minority carrier lifetime, and then you can solve this like you normally would, just plug in an x value and it'll arbitrarily spit out your solution once you have your general form.
I'm sorry. So I already forgot. For number 3, at x equal infinity, that's equal to the GL tau p?
Negative GL tau p here.
Okay.
And the reasoning there.
Use the general equation for that, right? And plug in infinity. That's how we got there?
Yeah. I can go back to the general and I can just sort of explain it. So
that
was spatially dependent, so we can do this one. So and what you're asking for 0 or you're asking for infinity there? You're asking
infinity
for infinity. Yeah.
For 3.
So at change in p, x equals infinity, this part will go to GL tau p. This at infinity is equal to GL tau p, regardless of what happens over here. You can immediately say this is GL tau p simply because I think of it as it's approached the steady state of spatial condition.
Okay.
So this goes at infinity, it goes to GL tau p. Then this at infinity zeros. This at infinity is b times infinity, and then you have GL tau p. Okay, so now what does that tell you? That tells you b is 0. Cool.
And then using the same equation for question 4, you have at x equals 0. And it tells you what that is, right? It tells you it's 10 to the 11th or whatever.
Yeah, at x equals 0, it tells you 10 to the 11th. And I
have
this.
But then you have x equal infinity, and you just have to know that that's equal to 0 because no light penetrates, I guess.
Well, it says
yeah.
Question 4, it says it in the problem, doesn't it? Like, it tells you that the answer is going to be 0. Well, it kind of hints to it.
Yeah. So my answer for question 4b, when it's asking that, This is what I wrote. I wrote at x equals 0, change in n is equal to 10 to the 11th. And then I wrote at x, like that interval, like 0 less than x less than infinity, I wrote change in n equals 0. That was my answer for part B of the homework for question 4. Okay. Because that's just reading the problem. Like, there's no trick for that. That's just you got to understand how to read the problem and how to pull information there. Because if you don't understand the fact that, like, if there's some variation of no light penetrates past this point, like past this x value, if you don't understand that, you won't be able to come to that conclusion unless you essentially guess. So you need to know when to have your 0, 0 or your infinity 0, but you'll always have one of those points. You'll always have a 0, 0 solution or like an infinity 0 solution.
Okay.
Depending on the question.
And the other one's probably going to be given somewhere.
Yeah, the other, like one of them, like your 0, 0 condition or your infinity 0 condition is something you pull right from the problem. No math required there, really, for the most part. Math only comes in when you use those initial conditions to solve for your A's and your B's. So that's not a problem. Yeah, what is this? Q2. Q3 starts in my hand. All right, I just don't want to get my homework out of order. I don't staple these. I saved them.
So if it's not specified, one of the solutions is going to be 0 and the other one's probably going to be GL tau P.
Yeah, here I'm going to run through this thing and I'm just going to read the problem, and without doing any work, I'll try and tell you what the initial conditions are.
Okay.
So looking at question 1, I see T's, it's time dependent. It was dark at a time less than 0. And obviously at time equals 0 is when it was turned on. And then it results in some rate. So what we have first is a light source was turned on. At time equals 0, the excess carriers are 0. The light's on, but there hasn't been enough time for carriers to be produced yet. So your first initial condition, at time 0, what is this? This is change in P. At time 0, change in P equals 0. Then your next part, at time equals infinity, your change in P is going to be equal to GL tau P, because that's what when it comes to these questions in every single variety of the question, GL tau P is the max value you approach.
Okay.
That's the most amount of excess carriers you can produce using light. It's GL tau P. It's a relationship between the optical generation rate and your carrier lifetime. So that's it. Your initial conditions are either going to be zeros or GL tau Ps. That's what you got. So there's that. So that first one, this initial condition is at time equals 0, change in carriers is 0. At time equals infinity, change in carriers is GL tau P. Let's move on to number 2. Number 2, instantaneous uniform penetrating pulse of light at time equals 0. The pulse has 0 duration, but introduces this many excess holes and electrons instantaneously throughout the sample at time equals 0. Solve for the recombination rate per unit volume as a function for time like this. So what ends up happening? What do we do here? So the initial and boundary conditions for this problem were trickier because this one sounds ridiculous, right? It sounds like some random non-possible event, a 0 duration thing that instantaneously introduces this many excess holes and electrons throughout the sample at time equals 0. But here's what it's telling you. That means at time equals 0, what did you predict? And here's something
10
that's
to the 12.
Yeah, you're right. But here's something that's important to tell you here. It didn't tell you what GL tau P is here. But like later on, you basically make a bunch of assumptions that essentially means that, oh, look, this ends up being that. Who would have thought?
Oh.
But so yeah, you're right. So at time equals 0, what's your initial production? 10 to the 12th. Cool. What happens at time to infinity? Oh, it's 0.
And why is it 0 again?
Well, why is it 0?
Yeah, so there's something that's interesting, right? So instantaneously, think about it this way. So what number, like question 1 was a graph that looks like this, approaching GL tau P. This question can be treated as a graph that looks like this.
Starts at GL tau P.
Starts at GL tau P, or the given number here goes to 0. Those are the only 2 scenarios we have. As of now, that's all we have. It's one or the other. There is no other.
It must be because the pulse of light has 0 duration, so GL goes away after 0.
Yeah, that's why it happens.
Okay, that makes sense.
So this is just a really weird wording of saying the light has been on for a long time. essentially, even though it's not the light has been on, it's telling you it's some impossible instantaneous light flash. But this type of question is indistinguishable in terms of working it out as the type of question where it's like, light has been on for a long time, blah, 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 like that.
Okay.
So does the light start off being on? Does the light start off on? Or
the light starts off with a penetrating pulse of instantaneous light that's uniform. But the thing is, obviously, the reason that he had to phrase it like this...
Because I'm visioning, like, the graph of... I'm trying to, like, imagine the graph in my head. You feel what I'm saying? So, like, I know the graph is going to be, like, an exponential, like a, you know what I'm saying?
Yeah, yeah. So here's how you can look at it. So question 1, it goes from 0, 0 up to GL tau P. Question 2, it goes from 10 to the 12th, or what we would normally call GL tau P. It goes from 10 to the 12th down into 0. So GL tau P down until 0. So literally, if you look at it, it's if you mirror it across the halfway point, it's mirrored across the x-axis, flipped up or down for these graphs.
And in this case, if for whatever reason we had to graph it before time 0, it would be 0 the whole time, and then it would just
jump
up.
It would literally look like 0, 0, 0, 0, instantaneous spike to this point, like literally like a step function, then back down.
Yeah, got it.
Yeah. So then this one, we look at this Q3. We have, what is it? It says, so it says X's. I know that means we have spatial stuff. So here's where we get information. Surface at X equals 0 is damaged. Minority lifetime is 0. Okay, there's no carrier lifetime. There's no carriers. 0, 0. There's your first thing. At X equals 0, change in N or change in P. Let's change in N here. Change in N equals 0. Beyond 0, beyond X equals 0, the minority carrier lifetime is, constant given value. Tau N is equal to 10 times -7th. What does that mean? Well, beyond X equals 0, at X equals, infinity, we can just say that. At X equals 0, change in N is going to be equal to GL tau P, because that's the maximum value it can reach. And even though the word steady state, isn't right to describe, something that's spatial, I still when you think steady state, it means it's reached its stable condition, right? It's steady state. So I think of this type of question when it goes off to an infinite space that way, when it's spatially dependent, that it's reached its steady space or something like that, where it just stays at some value. And that value it approaches every single time is going to be GL tau P, unless specified otherwise. Like in Q2, it gives you some number. But for our, it's just still the same idea.
So for this one, it's at X equals 0, it's 0. And then at X goes to infinity, it's GL tau P.
Yes.
Yeah.
And then this one is the exact opposite. So instead, at X equals 0, change in N, or in this case, change in C, is equal to 10 to the 11th. And then at X greater than 0 to infinity, so at X equals infinity, change in carriers is equal to 0. Nothing's happening. Just a straight up inverse. Questions are asked a little bit different. You're given new numbers, new variables, doesn't matter. Same process. And in this case, the same thing. The graph looks near identical to this types of thing. So you look at this like a graph of whatever this to X. If you were to graph carrier densities versus X, or carrier concentration versus X, or excess carrier concentration versus X. For question 3, it said it started at 0, right? Yes. So at X equals 0, carriers are 0, and then it goes up and approaches GL. This one starts at 10 to the 11th, and then goes down to 0 exponentially. Same function. So yet again, draw a line down the central point of that graph. It's mirrored across the x-axis. Same thing.
Wait, go back, because that one didn't click like the other ones click. So you saying that our conditions here is also going to be 0 and infinity?
For this one, yes. For question 4.
Question 4, okay.
Because what it says,
when it's 0, the answer is going to be 10 to the 11th.
Yeah.
And you know that because it says excess carrier at X equals 0. It gives you that answer.
Yeah, this one just tells you. And then it also, the questions, the trick is you don't need to do math for to set up your conditions, because the conditions should be given in the problem. If they're not given in the problem, you're either missing something or something went wrong when they were writing the problem.
And I'm guessing that when x is infinity, the answer is going to be 0.
Yeah, because look, no light penetrates, past 0. Therefore, nothing's happening. No excess carriers are produced. 0. So that's how that works.
Okay, how do you do question number 8 on the practice quiz? Unless someone has more questions on this.
I can get quick question 8 real quick.
I have a few practice quiz questions too.
Yeah. All right, we can do question number 8. So net recombination rate is actually a formula that's given. I could go over the PowerPoint, but I'm pretty sure I remember the formula. R net is straight up equal to GL times your tau value.
Whichever minority, right?
Yeah. Everything's always
working. There's a formula for this, right?
Yeah. I'm telling you the formula. I'm pretty sure that's it. I can go over and confirm it in PowerPoint. I know it's there.
I'll eat some soup later. Thank you.
Right here. Wait, where was it? Never mind. No, that's wrong. It's this. I was thinking of a different formula. This is it. Net is equal to your carriers. The amount of carriers divided by the carrier lifetime.
Oh, okay.
So in order to solve for a question like this, you need some value t or x, depending on what you need to do. To confirm that, let's go look at the quiz and see if it gave you a value of t or x. Oh no, it gave you a tau value. What do you know? And it gave you a value here. So look, you can look at this one. Interesting. So look at this. Calculate the net recombination rate at t less than 0. Question 8 is an instant recognition problem. There's no math to be done here because this question, that type of question, I doubt it will be asked on the actual test, because looking at this question, the sample was in the dark, or the sample was in dark under thermal equilibrium for time less than 0. If you're in the dark and under thermal equilibrium, nothing's happening. So that means everything can be done or performed normally, like we would have beforehand. There is no recombination. There is no generation. So the net recombination rate at time less than 0 is 0. So that's 8. But then the trick is 9 is something similar. Like this is the one where it actually takes like more doing. So look at this. It gives you some time value, which is 1. And remember, 1 is 1 compared to like 10 to the negative 6 is huge. So this is going to result in our, value of, change in P being equal to GL tau P here. And remember, what happens is R net, as we just saw, is equal to the carrier density or the excess carrier concentration divided by tau P. Right? Yes.
Yep.
Because of that, and oh yeah, this is what I'm saying to say it. Because what happens is, as we just saw, because it tells us at time is equal to 1, we know that this ends up becoming GL tau P. So our carrier concentration is GL tau P. GL tau P divided by tau P is GL. And now your R net, which is now just GL, divided by GL is equal to 1. And you can see that the right answer is 1. He gave you some wiggle room of 0.01, but the answer is 1. So you see this like divide by GL thing, that's just him adding extra algebra on to just see if you basically know what you're doing with like terms and variables and stuff. But he could have just said calculate R net and it would have just been equal to GL, which happens to be 10 to the 18th in this question, I believe. Any questions on that one?
I think that makes sense.
Yeah, it's just like that.
It didn't fully click with me though. I'm not gonna lie.
All right, so
the first one when the time is given to you. Okay, so when t is less than 0 seconds.
Yeah.
You got 0. Well, so you just plug that in.
You don't need to plug it in at all, because remember, in this question it tells you at time less than 0 the sample was in the dark and under thermal equilibrium. Because of that, no generation and no recombination. Remember, all this stuff, all this MCDE, everything here is predicated upon the concept of generation and recombination.
Okay.
In this case, due to optics, like light. And because at time less than 0, there is no generation and there is no recombination, how could there be a recombination rate? It's not happening. It's 0.
Okay, cool. What question 9 when they actually give you
Yeah. So question 9 is a bit different. So what you do is now you take that 1 and you plug it into this formula, that we got up here, this one. And if you look at this, 1 divided by 10 to the negative 6th is a big, big number.
Right, so go to 0, right?
Big, big negative number goes to 0. So your excess carriers end up being just GL tau P.
Okay.
So you take GL tau P, you bring it down here. GL tau P is now equal, R net is equal to excess carriers divided by tau P. So this becomes R net is equal to GL tau P divided by tau P. Obviously, tau P's cancel, just becomes GL. R net is equal to GL. What's GL divided by GL? It's 1.
Wait, so you just did, so scroll back up to the top. I'm sorry. Scroll back up to the top real quick. So yes. All you did was you got GL. I understand this. So you got GL tau P for delta P. So scroll back down.
Yep.
To where you was at. Okay, so you got R net over GL. So you're going to substitute GL tau P where R net is at?
So R net is solved this. It's solved by excess carriers divided by the carrier lifetime.
Okay.
Just so happened our excess carrier happened to be GL times tau P, so those tau P's are going to cancel.
Oh, and just GL. Okay, I got you.
And then it leaves with GL. So if he was asking for just the R net, our answer would be GL. But he's not. He then divides our R net by GL. What's GL divided by GL? It's 1. And you can see that that's the answer. But he just put like, you know, like a thing between 0.01 to either side.
Okay.
So yeah, that's how that's done.
Okay. And then for 10, you just plug in 10 to the minus 6 into the P general equation?
Yeah, the equation we just scrolled up to. What's 10 to the minus 6 divided by 10 to the minus 6? So 1. Negative 1. What's e to the negative first? It's like 0.36 or something. Now, what happens then is if we go back up to the equation, this is one we actually have a value and it doesn't just 0 here. So it ends up being 1 minus like 0.3, like some decimal string. You'll have to do this in the calculator.
You have e to the minus 1, right? I'll do it.
Yeah, e to the negative first.
0.37.
Yeah, now do 1 minus that number, whatever that is.
Yeah.
Then you take that and you multiply it by the GL tau P value, which you don't need to do GL tau P, it's just 10 to the 12th.
0.63.
Boop.
So 0.63 times
Boop.
10 to the 12th.
Boop. Boop.
But why is it between 63 and 64?
So you got like something point, right? I remember something here. It's because you divide the P by Ni, because it says find the values of P divided by Ni.
Oh, GL tau P is 10 to the 12th for this one, right?
So yeah, so do 10 to the 12th times, you know, that decimal that you get.
0.63.
And then divide by 10 to the 10th, it's going to be 63 or something.
Oh yeah, 0.63 times 100, yeah. Okay.
There you go. And that's how you get between 6.3 and 6.4.
Got it.
That's a question, because as you see, that's worth 10 points. These 10-point questions are the type of questions you might see on the test. Like these 5-point ones are a toss-up in my opinion. These are the type of things that might not show up. But these 10-point ones, well, this one will show up. These 10-point ones are the type of ones that'll show up. And this one will also show up. Where were we? We just did this one. How about this one? Calculate the ratio of R net at a different time. So we just went through the process of solving R net at some arbitrary large time. In terms of our time scale, which is in microseconds, 1 second's a long-ass time. So R net over GL, that's what we did here. The same exact solution, like same solving way here, but at a different time. So as you just said, you know, 10 to the negative 6, e to the negative 1 is like 0.37. So you do that whole process again, you get a different excess carrier value. And look, you see this right here? The 0.62, 0.64?
Yeah.
This is what you just got instead of without like the NI part. Instead of it, because look, the process that's different is you do the R net here ends up being GL tau P times that 0.6, like 0.6 value.
Yep.
So then GL tau P times that divided by tau P, you're going to get rid of the taus. Then look, he divides the GL, you lose your GL, now you're just left with the 0.63 or whatever. And as you see, that's within his answers, so you're good.
So what equation will we use for that one? Will we use the same one we just used before with the delta P over? Okay.
Yeah. So this one, right here on the PowerPoint, this equation right here, the R net equation.
Okay, cool. But okay, yeah, okay.
So this, that is music. This.
Night chord.
You bet your ass, homie. So this, where was it?
1, 2, 7, 3.
Where was, right here. This question, you solve it the exact same way as this question. You just plug in a different value for time. And it changes.
So does the GL? So do the GL still be the? It's still gonna just be GL. Like, well, why does the not end up being the same?
So you can look at this question. So here's
the different stuff cancel out.
It does end up canceling out. The reason it's 0.6, like 0.63, is simply because that time value is different. So it ends up being GL tau P times 0.63 as opposed to being times 1, because the E actually amounts to something besides 0 in this scenario. And because of that, it becomes 0.63 times GL tau P. And remember, to solve for R net, you take that tau P away, they cancel. Now you have 0.63 times GL. And look, you okay. GL, you lose your GL, now you just have 0.63. You're done. And that's how you solve. Look, it's within his answer tolerance. So that's the correct answer. Question 12 takes it's just plug and chug. Just plug and chug doing.
What is the equation, if you don't mind?
It was displayed somewhere in his solution sets. Here they are. So here's something, I'll explain this as you'd like get these down. So copy these first portions of the equation, like identically, like leave all the equals out, because obviously that's him solving for something. This equation and this equation are the equations you're looking for. But keep in mind that the minority carrier, like if your P is the minority carrier, then NA is going to be the change in P instead, and this would be ND. And then if N was your minority carrier, you know, the ND would be this, the change in N. So you just got to make sure that you know to replace those. And then you also need to remember that FP has a minus sign and FN has a plus. But obviously you can do this on a formula sheet.
Oh, I didn't even notice that.
Yeah. So here's the reasoning behind that. FP, so EI is your, your middle level. FP is your holes. It's going to always be lower than EI. Lower or equal to EI. So that's going to happen. So it's going to be minus. It's EI minus to get down to that level. Fn is your electrons. It's always like higher than or equal to EI. Therefore, it's going to be EI plus some amount of electron volts to move that to the quasi-Fermi level. And that's how those work. That's the reasoning behind the signs. You really don't need to like super understand that unless you have to graph it on the spot. It's good to know because you're going to want to know it for the long run. But as we see on the exam, unless he gives us a multiple choice with pictures, we can't draw them ourselves on that because the exam's limited. On like a handwritten test, I assure you he would have had us draw them, but we can't do it here. So instead, you just have to he's going to give you a question like this that just tests that you know how to get like the right value of Fn and Fp by just arbitrarily subtracting them from each other.
If it was an N-type, go back to the example. If it was N-type, would the signs change or would the...
Nope, signs never change. The only thing that changes is the numerator. Yeah, the numerators change. And if you need further, I'm pretty sure this type of stuff I went into more detail on this stuff for in the long video I have, which we did yesterday.
Okay, so for this one, so for 12, how do you know what delta N is? Because it doesn't tell you what X value to plug in or anything.
It gives you a hint. It says at steady state. This is time dependent, so it's GL tau P. You assume it reaches GL tau P.
Okay.
So at steady state is infinity. That's what that means.
So for Fn, for this one, for Fn, it would be Ln of infinity over.
No. This is I believe FP is the minority.
Oh, okay.
So Fn, I believe ND in this question was 10 to the 18th. So it's 10 to the 18th divided by 10 to the 10th, which becomes obviously 10 to the 8th. So it's ln 10 to the 8th times all that stuff.
Times 0.026.
Mm-hmm.
What do you do with EI? You just kind of leave it there?
I carry it through to my solution because that there, I talked about that in the other video. That there is strictly there for our benefit in terms of helping us figure out how to graph it properly. Well, if we were, had to illustrate it. But we don't have to do that here. So the EI is really doesn't, like, it's not that important right now.
Okay, so the FP would be EI minus whatever constant value. And then Fn would be what's ln.
Here, I got this. I remember the formula and everything, so I can do this. So we have 0.026 times ln of, let's do Fn first, which just so happens to just end up being 10 to the 8th power. What does that give me? It gives me 0.47 or something. Then we do 0.026 times ln of Fp, which is GL tau p, which is 10 to the 12th divided, so that's 10 to the 10th. 10 to the 2nd, sorry. 10 to the 2nd. Now, can you see that? What happens? And remember, Fp, this is where the sign does matter, though, because Fp is lower, so subtracting Fp when our reference value is EI is going to be minus minus plus, so it becomes a positive, so you add it. So in this question, the way he's asking it, that negative value does matter because Fp is negative. Its reference is negative because our reference is EI. So what ends up happening? What happens when you add 0.478 whatever to 0.11 whatever? You get 0.5986. Oh boy, that's within the tolerance. So that's the right answer, or an acceptable answer. So the trick with this problem is not messing up that sign on the FP. Because if you mess that up, you're donezo. So I said earlier, like when we go back to the PowerPoint, I said that like the EI thing is for our benefit for physically graphing it. Because at the end of the day, when we actually, let's go down to this, when we actually look at this like figure, these values are positive values. They're both positive values because obviously it's an amount of energy. We're not losing energy here. In both instances, some amount of energy has to be gained to reach that level from your valence shell. But the thing is, our reference value is set at EI. So that means there's a stark difference. There's a positive and there's a negative. And because of that, Fn minus Fp is actually Fn minus a negative of Fp, which ends up being Fn plus Fp. And when you compute those numbers, it gets you some value that's within the tolerance for the correct answer for this problem.
Okay. Sorry, I'm going through this a little slow. So the first one, it's going to be EI minus 0.026 ln.
No, 0.0026. Remember, 0026.
Wait, really?
It's 0.026. It's not point. Wait. No. It's, yeah, right there. Right there. I might have misspoke there. It's 0.026.
Okay, gotcha.
Yeah.
And then times ln GL tau p over Ni. That would be for FP in our problem.
Yes.
And that would be 10 to the 12th over 10 to the 10th.
Yes.
So whatever constant value that it becomes negative, it's still a negative number, right?
Yeah, that's going to give you the number 0.1197 whatever, and then you're going to treat that as negative. You're going to treat that as negative.
Okay. And then the other one would be ln 10 to the 8th?
18th.
Over 10 to the 10, right?
Yeah, so 10 to the 8th, so ln 10 to the 8th times 0.026.
Let me type that in my calculator.
Mm-hmm.
Ln of 10 to the 8th. 0.48, whatever.
Yep, close enough.
0.48. And then you said
Yeah, because what the question on the quiz was asking, it's asking for Fn minus Fp, but as we said, because of how we're referencing to EI, the Fp value we calculated with this equation is going to be like negative, so it's going to be negative like 0.11.
Yeah.
So then obviously 0.4 whatever minus a negative is going to be 0.4 whatever plus the value.
Oh, that's kind of tricky.
That's why that question's weird. That's why it's a little weird, because if we were taking this test by hand, like in class written, like no COVID, it'd be completely different. Instead, we would be asked to do this and then draw this figure. This is what we would do.
Right. That's what we did on the homework, right?
Yeah, we did it on the homework too. But now, since obviously this is not something that's like a viable thing that you can do, because doing it this way and making a multiple choice question out of these figures is obviously not a good idea, because of the nature of how this works, you can basically go back and guess and check your quasi-formula levels because those values are given and you don't have to do work.
Yeah.
So instead, it's better to keep it like that and just say, because Fn minus Fp, as far as I know, doesn't give something that's useful. It's just a number. But that number being correct is dependent upon your understanding of how to calculate Fn and Fp being correct. And it's a good way for him to use an open-ended method that still makes it difficult for the student, but allows him to test your knowledge anyway, in an abstract way.
Okay. I suppose the hardest part of question 12 is knowing that delta P at infinity is GL to LP.
Yeah. Well,
or just knowing that it's at infinity.
Yeah, but because of the steady state part. But by question 12, you should understand that, hopefully, assuming you were doing it correctly up until then. Yeah.
I guess it's just knowing that it means at x equal infinity.
Yeah. Well, in this one, it's time, but yeah.
Oh, okay.
Yeah. So then here we have another thing. If the light is turned off at time is equal to 1, calculate the whole density at time is equal to 2.
So GL goes to 0, and then you plug 2 into your general equation?
Yep.
Would you need to know A for this?
Well, actually, here's what you can do. So remember, the A is already solved, remember? So this isn't redesigning the equation. You could technically use the one we have, but this is a theory question. Because think about it this way. Lights off, and remember, these changes happen in the order of microseconds.
Yeah.
We have a whole second from when the light turned off to where we are now.
Oh, I totally skipped over that.
Because of that, it's basically back where we started. It's at the same exact state as we started at, which is in the dark and at thermal equilibrium. Question 13's answer is 100. Let's go all the way back up to the beginning. What's the whole density at time less than 0? 100. It's back to where it started. And it always goes back to where it started. Unless some physical structural changes happened, it goes back.
And that was based on the mass action formula.
Yep. You can use mass action here again.
I go about these like I like to solve them algebraically, and then it makes sense to me theoretically after that, you know.
Yeah. Everyone's got their own way.
Yeah.
And then here, look, this question 14. This is just a theory question. I've been saying it this whole time. If the light is turned down at time is equal to 10 seconds, how long does it take to reach thermal equilibrium?
Okay. Well, how would you know it's not nano?
Okay, so nano's pretty quick, because remember, that's another like 3 orders of magnitude faster than micro. That's pretty fast. The reason we know this is because he said it once in lecture. Okay. And also you can see because the carrier lifetimes are in the order of microseconds most often. So we've been dealing with holes quite often. And holes, of course, by nature, like the positive, variety of the carriers that we have, they have a longer carrier lifetime than electrons, who tend to be to like 10 to the negative 7th.
Yeah.
It's just the nature is like a hole and an electron, while they have equal charge, the same way a proton and an electron have equal charge. There's a difference in like mass there, I'm pretty sure. Like there's a physical reasoning behind why holes have a longer lifetime, and it's because their reaction is slower.
Well, I guess it would be shorter, or no.
Longer. It's longer.
Yeah, lifetime. Longer. So if for whatever reason he said that TP is 10 to the negative 9, then it would be nanoseconds.
Yeah, then it would be, but we're not there.
But he's probably not going to do that. Okay.
No, as far as we've seen, it's always, they've either been equal to each other, or the holes have been to the negative 6 and the electrons have been to the negative 7th. Because that is I think he said it was a material dependent parameter or something like that, which makes sense.
Yeah.
because that type of lifetime probably there's a lot more physics and chemistry and material science there than I'd care to get into.
I'm just concerned about passing the class for right now.
Yeah. I'm a first semester sophomore. I'm taking this class without a prereq, and I was terrified when I started. But so we're done with review, so I'm gonna stop recording.
Okay.
Because this obviously ends up getting posted.
Are you a TA?
Nope.
Oh, well, you are